Hey everyone, back in a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will introduce torque. We will relate it to angular acceleration to find the circular equation of motion. After that, we will use an example to find the torque generated by gravity, and then we will see how the Newton's third law behaves for torque. So let's start. Wait. Torque is the analogous in circular motion of force. It is defined in the following way. Torque, it's a vectorial quantity, and it is defined to be the cross product between the position vector and the force. So, for example, if you have some object and you have over here the center of mass, which is going to be its axis of rotation, and you are putting a force over here, the torque is going to be the cross product between the position from the axis of rotation to over here with this. And you can also find that as it's going to be a cross product, it's going to end up pointing outside or into the page, into the whiteboard in this case. So it's also going to follow this k-hat rule kind of we had for angular velocity and angular acceleration. Now, let's examine the relationship between this quantity and angular acceleration. First of all, we need to consider that the torque relevant to this situation is going to be the one that points up to the k-hat direction. We're going to write our coordinate systems with r hat and theta hat. So our force for this small particle Fj is going to have three components. So Fj, it's a vector that's going to have an r component, a theta hat component, and a k hat component. By doing some calculations using the definition and noting that we only care about the torque in the k-hat direction, we see that the only one relevant is the torque in the theta hat direction, because in the r hat direction, r hat with the r hat is going to give us 0, because it's the cross product of two parallel vectors. R hat with the k hat, is going to give us a minus theta hat direction, which is not the direction of torque we are looking to. But theta hat and r hat, they are going to give us a k hat direction, and that is what we are looking forward to find. Now, therefore, we see that for our z component, that is what we are looking to, the z component of r hat cross f j external, what we're going to find is only rj times a theta comma j, because they are also perpendicular, and this is going to be in the k hat direction. So let's make it a vector. Great. Now we need to find an expression for this force, and remember from Newton's second law that the force external on an object is equal to this small chunk of mass that is being acted on times the acceleration. So it's going to be acceleration external j, and this is going to be a vector. As we are only taking care of the theta hat component, we're going to have that the theta component is going to be equal to this mass times the acceleration in the theta hat direction. And you may realize, and similar to what happened with theta and the position along the arc, the velocity in the theta hat direction and the angular velocity, we have a similar relation with the acceleration in the theta hat direction and the angular acceleration. That is that delta mj times r times alpha j equals this. You can easily find this because bj equal in the theta hat direction really equals wj times rj. Therefore, if you differentiate this with respect to time, r is going to stay constant. Therefore, you would find that this is the acceleration theta j, rj, and alpha j. And that's the relationship we have found. Now, knowing this, we may substitute this expression for f theta j in our equation for the torque in the z direction. So we're going to do this. Z direction equals delta, rj times delta mj rj, we're going to square it, then time j now, and alpha j in the k hat direction. However, we're only considering a small chunk of mass because this is only of j. To do so, we'll need to take the sum to consider all of the mass we have, all of our rigid bodies. So the total torque in the z direction, and let me start omitting the vectors, is going to be delta mj, the sum over j of delta mj, rj squared times a. And note that a, even though I've been writing these j's, it's going to be independent of j. All of the different masses of our system have the same angular acceleration. They have different accelerations but have the same angular acceleration. Now, knowing this, what we are going to do is to take this and take the limit, as we did on the previous video, as delta mj goes to 0. And if we do that, d of z goes to the limit as delta mj goes to 0 of this sum from j, delta mj. These two don't seem like j's. Delta mj rj squared times acceleration. And if you remember correctly, this is going to give us an integral over dm of r squared times alpha. And this is no other thing than the moment of inertia. Therefore, we find that the torque an object feels, it's going to be equal to the moment of inertia times the angular acceleration, which is the circular motion equivalent of Newton's second law, F equals ma. Great, now let's apply this to an example and try to find the torque that this object feels because of gravity. As always, we're going to take a small patch of mass mj and of the particle j, which is going to be at a point rj, and we're going to have over here our usual center of mass, which is going to be very relevant to this situation. So for this case, the torque that from the axis S that is being felt is going to be equal to rj cross the acceleration due to gravity, which is mj times the acceleration, the field, gravitational field. Now, what we find with this is that to take into account everything, we have to do once again a sum that is going to be the total torque, total from on the x-axis. It's going to be equal to the sum of rj cross, well, let's move the mj to this side, cross g. So we have a quantity over here, and this might be a pretty familiar quantity, and that is because we have seen it earlier. If you recall from the definition of the center of mass position, we had the sum from our, let's call this S to make a distinction between the center of mass frame and the S frame. So it will be the sum of RSJ times the masses, this is a vector, divided by the total mass, the sum of MJ. This is the sum over J. And if we solve for this, which is the exact same we have up there, we find that that equals the total mass times the center of mass. So we may substitute that into our equation, and we find that the total torque in the s-axis is going to be equal to the RCM. Now we're going to move the MT through once again, times the J vector. And what we see is something very interesting, and that is that the torque that the whole object feels due to gravity is the exact same than the torque a point particle in the position of the center of mass with the mass of the whole object would feel due to gravity. So once again, we can make in here our point particle assumption. Wait. In this video, we have already talked about the first law of Newton for circular motion, more or less. Object doesn't rotate if there is no torque applied to it. Then we have given an expression of the second law of Newton with these circular variables we use, circular magnitudes, torque, moment of inertia, angular acceleration. And now we're going to go for the third law of Newton, that is forces and action-reaction, opposite forces, which is going to equal to opposite torques. So if we have two particles in here, they are going to feel a force on each other, Fij and Fji. And we have over here this vector joining them, Rjs. So we know from Newton's third law that Fij is going to equal minus Fji because of action-reaction. That's just how it works, and as we saw in our video of Newton's law, this is a manifestation of the conservation of momentum. Then knowing this, we can find an expression for our torque. The torque due to these two particles attracting each other is going to be equal to first force times the first quantity, so RSI cross Fji plus RSJ cross Fij. Now we know these are opposites, so we may substitute one of them in the equation to get rid of one of our variables, and we are going to also take the common product of those. So we have RSI minus RSJ cross Fji, all of it vectors. And now what we find is that this vector is going to go in this direction. And this other vector, the vector's forces, also goes in the same direction. Therefore, they are going to be parallel or anti-parallel, but in any case, the cross product is going to equal 0. And what we have found here is that there is a torque cancellation. Internal torques cancel with each other in a similar manner to how in systems of particles, the different forces cancelled with each other and they didn't change momentum nor acceleration or anything of the system. So that's the exact same thing that happens in this situation. That is all for today. I hope you understood everything and that now you got a sense of how torque plays the same role as force in this circular motion world. Any doubts left, you may ask them in the comment section and I try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!